you. Thank you for starting that round of applause. So I'm from Stream Native. For those of you who don't know us, we're the company behind Apache Pulsar, which is a competing technology to Kafka. It's an enterprise messaging system. And obviously we were architected originally. We used Zookeeper as our metadata store, and we found that to be a bottleneck within our architecture, as with most people use Apache Zookeeper. We watched the Kafka community build KRaft, their solution, their alternative to replace it, and we unfortunately was not a solution that was widely adoptable. It was very tailored for Kafka, so we built our own called Apache, or it's just Oxia. It's Apache licensed. Where it's going to end up as far as community is yet to be determined, but it's our alternative to Zookeeper, and we were able to replace it. So a little bit about me, watching the self-promotion talk this morning. Interesting fact, I was the second professional services hire at Hortonworks. Those of you who don't know what Hortonworks was, we were one of the original 2 big data companies on Hadoop. Cloudera was the other one. They've since gone on to merge and become one large behemoth. But as part of that process, I traveled the world developing big data solutions and using Hadoop, Hive, HBase, everything, every one of those. And what they all had in common was they used Zookeeper, so it was the bane of my existence for 5 years. And every customer who used it was kind of impacted by that. The performance had issues with that, and that became one of our bottlenecks. Eventually, I moved over to another company, started with Apache Pulsar, worked it through the ASF incubation process up to top level projects, a very interesting journey. Became a committer on that 2021. And my way of giving back to the community, in addition to code commits, I've written a few books to share my knowledge of what I've learned on Hive and Pulsar. And if you use that QWERTY code there on the left, there's an information wall, but you can enter information and get an electronic version of my entire book, all 400 pages, if you're interested in learning about Apache Pulsar afterwards. So real quickly, what we're going to cover is why Zookeeper got a bad reputation, and deservedly so. It had issues with that. It's the only distributed system that doesn't scale horizontally. That's kind of its nomer. A little introduction to what Oxia is, and get into the architecture, walk you through it, performance numbers, and to prove what we're actually able to do, and then the benefits we're able to reap inside the Pulsar project from using Oxia instead of Zookeeper. So quick review of Zookeeper. Who here has not heard of, anybody here not heard of Zookeeper? Okay, everybody has. So quick review on this, and to highlight why it has a bottleneck and why it can't scale horizontally, right? It's designed to have 2 types of nodes exist in Zookeeper: leaders, which are the only ones that can handle the writes. So right away, that's a red flag for performance. Horizontal scalability, having a single serialization point means you're not going to be able to scale. And then everybody else is a follower. So they can service read requests, and they try to be in sync, but they forward all the write requests that they receive going back to the leader for being written. So what Zookeeper has, the way to keep in sync, is their ZAB, or Automatic Atomic Broadcast Protocol, and I'll walk you through that very quickly just to review this process and why it's a very non-scalable solution from a networking perspective, among other things. So to say you're a random client, I want to update a piece of metadata inside Zookeeper, so I send the data out. I'm unlucky, I'm in one of the followers, so I get the data. The write request is then forwarded from the follower to the leader, so the data travels over there. The leader says, okay, I have a proposal. I'm the leader now. I'm going to create a transaction ID for this guy. Let's go ahead and send it out. Broadcasts it to all the followers and says, okay, this is the change. We're going to update this piece of data. Go ahead and change it. This is the transaction ID. Then each of those followers writes that proposal to their own transaction log. And eventually, based on different variables, they start responding back. They start sending acts back to the leader saying, I got it, I committed this transaction. And eventually the leader waits for all of them. This could take any amount of time because network latency and other things, but eventually all of the majority of the followers acknowledge back. Then the next process is, okay, now I'm able to, so the leader decides, okay, I have a quorum, I have a majority, I go ahead and do a commit to my transaction log. And then broadcast the commit notification back out to everybody to say, for those of you who didn't get it, now you can go ahead and commit it in your transaction log as well. Before it was a pending transaction, now I'm the leader, I say this is committed. And then finally, the leader who received the original request sends the acknowledgement back to the client saying, yeah, we got your data, it's been persisted, it's been updated. Right, so this is obviously not horizontally scalable. This automatic broadcast and consensus protocol requires 3 network calls between the leader and the follower nodes, right? As I walked you through, the leader sends it out to all the followers act back in sequence, and then the leader sends a commit back out. So it's a 3x problem, and so as you add more nodes, the performance gets worse. And the numbers bear that out. I'll walk through the chart that Zookeeper published here in a minute. So obviously this limits horizontal scalability. The other issue that limits vertical scalability is the way that they persist the data. So Zookeeper likes to serve everything out of memory. They have an in-memory database, and it's a well-known axiom of Zookeeper that disk is death, right? If you're forced to go read the information off your commit log, it's going to impact the performance of your application. So everything wants to be served out of memory. But still, in order to be a distributed system, you have to have checkpointing periodically so that you have this data available in case of a failure in recovery mode. That's still a requirement for a distributed system. So every so often it takes a snapshot of the entire memory tree, everything has a memory, and writes it to disk. It also performs some checksums and integrity checks to make sure that the data wasn't corrupted, and then flushes that information to disk. So obviously the amount of time required to perform this writing the data to disk is directly proportional to the size of the memory in the data tree, right? So you can't just vertically scale your way out of it. I was one of those people who was guilty of that as much as anybody else. Hey, Zookeeper's having a performance problem. Let's increase the amount of RAM available to Zookeeper from 2 gigs to 4 gigs to 16 gigs. And you're just kicking the can down the road, because once you try to persist a 16 gig file on a checkpoint, that's going to take a significant amount of time and huge pauses in the performance, right? So that's a big issue. So it's been well documented, a lot of studies on this, that 2 gigs is about the sweet spot for that. That's roughly the size of that in-memory database you can serve. Anything beyond that sort of starts negatively impacting the performance. So this is published, taken directly from the Apache site as of last week. This is their performance metrics, and what it's showing is the number of total requests being able to be served by different size node clusters, so 3, 5, 7, 9, and 13. And then on the bottom is the percentage of requests that are actually reads versus writes. So first I want to note that for 75% of the workloads, more or less fewer nodes perform better, right? So 3 nodes is kind of your perfect number. Everybody uses 3 Zookeeper nodes, and this is why, because you're not sure what your data set's going to be, and not till you get to about 80% does that curve start bending towards the 5 or more servers. But it also makes sense because you're serving mostly reads now, and so if you have static data set and there's not a lot of change, the readers, you can start getting that inflection point where it makes sense. Second thing to note is the writes per second actually decreases as the transactions per second increases. So with the 80-20 mix, where 80% of the writes or the transactions are writes, you're doing right there around 30K. Again, I'm extrapolating 24,000 writes per second is what you're actually getting. Now when you move up to the 40% mix, so 60% of reads, 40% of writes, you should be still, 60% of 40,000 should be 24K, but you can see you're slightly below that number. You're not quite meeting it, so you're starting to lag a little bit. When you get to 60%, it's really starting to impact, right? You should be going, you should be getting a much higher number than that. You should be getting 20,000 writes per second, and you're not. If everything was lined up and matching, you'd be where that blue line is, but your performance is impacted, and it's directly the number of writes. When you get up to 80%, off the charts, right? So it really starts bending down. That really, what you're only achieving if you reverse engineer that 80%. This is what we're getting 70,000 transactions per second at 80-20. That means 14,000 of those are writes versus 24 when you're doing it early, right? So your write curve is going in the wrong direction. So Zookeeper's boxed in. You can't really scale horizontally. You can't add more nodes to make it more performant, and you can't scale vertically. You can't add more memory to make it better. And so so what's the solution? Obviously, Kafka community went their own way with us. We decided to go this way again. This is the repo. Query code, you can get all that there. I also put it just in plain text if you want to go check it out later. All documentations, design, validation, proof is all written there for your edification. So what is it? It's our own scalable metadata store and coordination system, right? So it does everything that Zookeeper does. It does, key value stores, it does locks, distributed locks, naming, and all those sorts of things. But it was designed to be used for core infrastructure of any large-scale distributed system, not just ours. Ours would be first. We'd eat our own dog food, but we want to make this available for everybody. It's ASF 2.0 licensed, and it was created, again, by my company, Stream Native, as a Zookeeper replacement for Apache Pulsar. It's our answer to KRaft, like I mentioned before. It's our way of solving the Zookeeper problem for our particular technology project, but we also are making it available to the community writ large, because it's not limited to just Apache Pulsar. So let's walk through the architecture a little bit, and we see why we think it's horizontally scalable. So we'll start with it provides an SDK that provides your key value API. That's basically what you're doing. Put this value here in this namespace, write this value back out, read it out. It uses gRPC protocol, so you can write any client you want. Very easy to implement. Right now there's a Go client, there's a Java client. We use a Java client internally to replace our Zookeeper, but you can write it in any language you want. If you want to write it in Rust, go for it, like whatever, just as long as it's gRPC compliant. Next, and then the clients interact directly with the storage pod. So there's a series of storage pods that can handle the storage of the data. Unlike, just like the Z nodes there, but has a way to store data and they have their disks. What we use is storage pods, and those are horizontally scalable. Each storage pod is assigned some shards. It can be either a leader or a follower as well. So we also use a replica-based mechanism, but it's like a partition assignment. So think of it again like if you're familiar with Kafka, you get assigned, one's a leader of serving that topic, everybody else is a follower, and they distribute the load across the storage pods. If you need more storage pods, you just add another one in and you can distribute the load across them. So truly horizontally scalable because there's no limitation and it's clients writing directly to it. Only the leader can serve reads and writes, so it's sort of blocked. You go to the coordinator first, say I'm interested in writing to this namespace, who's assigned to it. The Oxia coordinator says go to storage pod 2, that's your leader, do all your reads and writes there, and everything happens. There's no other coordination between the scenes. That's just all it does directly there. And it also performs failure detection and recovery. So it is monitoring, it controls the locks, it is the locking of who owns which particular shard. And if somebody releases a lock, it reassigns another storage pod automatically, and so the recovery can happen transparently and the client continue to operate internally. Like I said, leader election is also handles for that, so that's what the coordinator does. And then it's completely, because it's based on Kubernetes, we designed this to be cloud native, so we assume that people are going to deploy this in the cloud. So we use a Kubernetes operator, and there's a configuration map that you can define and specify, hey, this is what I want it to do. And the coordinator persists this information to a config map, right? So all the internal state of who owns what and which shards are responsible for which one can be persisted outside of the system itself and stored in just a configuration map. And so you want to restart it, all that information is there. The K8s operator can read it, start everything back up automatically. Then last but not least, the Kubernetes operator we have a custom resource definition file that you can pass it in, and for example, you can say I want to have 5 storage pods to begin with. I want to have total 2 namespaces to be served, and each one have 3 shards and replication factor of 3. So you can specify this, and because it's a CRD, if you change it and do an alter, it'll automatically do it. So I want to add more storage pods, I want to add more replicas, I want to add more shards. You just make a change, you submit it, and the Oxia coordinator takes care of all the rest, and everything gets spun up, and you have more storage pods automatically. So this is why it's horizontally scalable, right? Because you can shard the data set. So there's no individual one single leader that's your bottleneck. The load is distributed across it, and if it becomes too much of a load for one particular of those storage pods, you can just split that shard into multiple shards. So you literally can just scale infinitely. There's no reason why you can add many more storage pods, and it just continues to handle that load. Right now we currently do hash-based, but we're adding additional things like lexicographic sorting, keys, alphabetical, things like that. It's sort of pluggable. Right now it's just hash-based sharding. And the number of shards for namespace is initially fixed, but we're adding automatic shard splitting on the roadmap very, very soon. And so this is why our storage is scalable, right? So systems like Zookeeper, etcd, all these other ones we talked about have that 2 GB limitation because of the periodic snapshots of the entire data set. That limits the amount of data you can physically serve, which limits the amount of metadata you can have, which is, for us, Apache Pulsar has some limitations. A lot of other people have limitations around that performance as well. We're able to get around that by putting data into a storage system. It's designed to store the metadata larger than the available RAM. So we use, I'll go ahead, next one here, log structured merge tree, key value store on top of the memory as a read through. So we're able to basically store or provide real-time access to over hundreds of gigabytes of data when only using like 4 or 5 gigs of data. So we actually have that mapping that the LSM gives us quite a bit of boost with that, but we still have the data written entirely on disk. And we don't have to do, because we do that, we don't have to do the snapshot every and number of updates. We can prolong the amount of time we do snapshots because everything goes to a write-ahead log. So this is how we replicate things. The other thing that made it easy is we don't try to re-implement any sort of consensus protocol. We don't need it. We discovered that instead we're going to use a different approach to data replication that's proven and tested and works well for us, and it's well proven out. So it's a non-fault tolerant log replication. Think of it like, again, Kafka or Pulsar. You publish data to one leader, it has a replica. If something fails over, you go to the replica automatically and you recover from that failure. So instead you apply a recovery protocol when the leader fails. And we have documentation on how this is proved mathematically to be correct. There's no data loss involved. It allows us to not have to worry about consensus protocols anymore. It makes our life much easier. We didn't want to rewrite Raft. We didn't want to rewrite Paxos because those are very difficult things to do. So again, as I mentioned before, read and write operations only go to the leader, right? So the client publishes to the leader. That data is persisted to a local write-ahead log, which is the most efficient way of storing data, ingesting data very quickly. You just append the data to the end. There's a local key value store sitting on top of that, and then the leader pushes the data. The local write-ahead log, and the leader pushes all of those entries to the followers. Whoever's allowed to be the followers, so it's a push-based replication instead of a leader-follower. It doesn't pull, it pushes. So the information gets there much more quickly. And then once the followers acknowledge back to the leader that I've gotten the data, then it updates its local key value store to say this is my version of the truth. And it also lets the followers know that they can update theirs as well. So that way, because they're fully committed, that makes the failover fast leader promotion very quickly because it has an almost identical version what the leader had at any point in time. And so it can easily switch over without any sort of recovery lost as well. So it's a very, very efficient way of getting the data replicated across. Let's see here. So some of the advantages of it becomes it was much easier for us to implement a log replication because it's something that we do every day at Pulsar compared to implementing a full consensus algorithm. Again, we realized we didn't need it, so that was our key insight to take that out and make things a lot easier. And we also separate the data path for writing the data, which is the write-ahead log, which needs to be optimized for speed, right? So have a different completely set of disks and writes there, from the recovery path, which is the log structured merge tree sort of mechanism there, so which needs to be optimized for readability and correctness. So we have different functionality of the disks, and we can optimize them for each one accordingly rather than having to use one disk for everything snapshot and recovery. And then last, we've offloaded the cluster status checkpoint entirely to an external source of consensus, which again is the Kubernetes. We just let that write it as a config map, so we don't have to store that internally as well. So it makes it much easier for checkpointing of the cluster status. And last but not least, let's get to the success of what we were able to see out of this. So this, based on our implementation of this, this is what we're able to achieve. So this isn't exactly apples to apples. This is what we have. We're testing now to see which compression algorithm has the best impact for our performance. But I want you to notice that for each one of these, the blue represents the number of writes, and the red represents the number of number of reads. And we ran this test using the 80-20 mix is what we're trying to achieve. So 80% writes, and or 80% reads and 20% writes. But you can see if you add those up, that's your TPS per that performance test. This is done with a single node acting as the shard leader and 2 acting as replicas, right? So this is just what one single node can do. And this is roughly, if you add those 2 up, you're consistently at 100,000 transactions per second. Just as a refresher to go back and look at that slide that we looked at a few whiles. Oops, sorry. There, that little blue line where it crosses at that same mixture. Pulsar. Zookeeper struggles. It can't ever cross 60,000, 30,000. It's really hard for it to cross this number. So we're able to achieve a much higher number of transactions per second using the same number of nodes on a single node. And that's a per individual node. So as you scale them out linearly, you can just add that on. If you need more writes per second, you just add another data storage node, again, because you're going directly to the client, and then it's able to scale automatically. There's no interaction between the two. There's no dependency between the two. So again, and we didn't sacrifice latency. So these are latency performance numbers using all the different compression algorithms, which you can see we're consistently always under 300 milliseconds. A lot of time, again, for the reads, well under 100 milliseconds, writes no less than 3x that. So very, very good performance numbers, and this is P99 latency very, very worst case scenario, but there is no sacrifice of latency for this. So in conclusion, from what I hope we take away from this is our direct impact, since we went and implemented this and tested it out, what we were able to achieve internally was get rid of Zookeeper entirely from Apache Pulsar. So simplifying the operation of the cluster. Right now we have, those of you not familiar with Apache Pulsar, it was a 3-component system. Pulsar is a stateless broker layer. Bookkeeper, which is another Apache project, was our storage node, which was stateful, but it was a separate storage layer. And then we had Zookeeper, which was our metadata store that let us know, basically, in addition to policy information, I'll talk about it here, is that we also, so we would have data stored in Zookeeper, and our metadata store kept the pointers to where the data was. So the way that you store data in Kafka is like partitions, right? So think of that like an array. I'm going to have 5 number of buckets, and that's what I'm going to have, and that metadata is controlled. We don't do it that way because that limits the amount of data you can store in an individual topic. What we did is like a linked list. So we have segment-based storage. And every 50,000 records or so, but it's configurable, you create a segment, boom, close it, create another one, create another one, create another one. So you just depend infinitely onto the storage. And the metadata storage, Zookeeper, is where we kept that information that said this topic is segment 5 and segment 12 and segment 15 and segment 45. But since we were limited to the amount of data we could store in Zookeeper, our topics can only grow so big. Now that we've gotten rid of Zookeeper, from a practical perspective, we can really store infinite storage. If you want a topic that has 800 million petabytes, no problem, right? Just put enough nodes in there to store it, and it'll do it. Because our one limitation has now been completely eliminated from the cluster. Another issue was that our number of topics being supported was limited by the metadata as well. So we had policies and information that was kept again in Zookeeper, and the ability to look data up to go grab that information out and pull it and read it was limited. And this is a point of reference. Before Oxia, when we had a Zookeeper-based cluster, we could maybe get 1 to 2 million topics supported on our Pulsar cluster with a lot of heavy tuning, a lot of specialization and tuning to get it to support that number. Now out of the box, we could do 10 million topics, and we're well on our way to 100 million topics very soon. So no longer have to worry about the number of topics or the way that you structure data inside your messaging system. You can have a topic per device, for example. You don't have to worry about partitioning and all these different things anymore. We've just eliminated those entirely. So in conclusion, we designed Oxia, a bit self-serving, but it was designed to solve our metadata scalability problem using cloud-native architectural design patterns, right? So we lean into Kubernetes quite a bit. We believe that these problems are common for other distributed systems that require everything that Zookeeper provides: synchronization, configuration maintenance, grouping, and naming, right? So anything that uses Zookeeper can probably benefit from what we've done, and it's very easy to port it over, we think. And so we think any Apache Pulsar any Apache project that utilizes Zookeeper has the potential to get these same benefits by switching over to Oxia. Again, I'm going to leave the slides there. You can go scan it again. For more information, go to the GitHub repo, try it out, read some more about the documentation, and that's it. I'm done. Thank you very much.